Hello. Hello. So I just wanted to share this really awesome question I did on my midterm for my algo class. And yeah, let's go over this. So suppose your company has like two offices, one in SF and one in New York. And each week you could choose either to be in like your SF office or like the New York one, right? And depending on which week you're at like a specific office, you make like a certain amount of money there. Um, so as you see right here in this table, on week one you would make 800 bucks if you were in San Francisco. Week two, 200, and so on. Um, yeah, and so you prefer to like work at offices such that you could maximize your profits throughout like a week. Well, throughout like n number of weeks, right? So you're trying to make the most amount of money in like the weeks that you have. So to do so, you're able to move between cities. Like if you're in San Francisco, you can go to New York and vice versa by taking like a plane. And assume that like a plane ticket costs $1,000 to go between the two cities. So your task is to basically figure out what's like the maximum amount of profit I can make traveling between these two cities, um, between like n number of weeks. So right here, here's like an example. Like suppose you also start off at San Francisco too. So suppose I'm at San Francisco. I'm gonna work the first week in SF. I'm gonna fly down to New York and go work week two and week three and week four in New York. Then I'm gonna fly back to SF to work um, the last week there. And the total profit I made was 3,600. So yeah, describe an algorithm to compute the maximum profit, assuming you start off at SF. The input to your algorithm is going to be like a pair of these arrays right here, um, which contain the profits for each week. So I've actually have not coded this yet. All I've done is kind of write out the pseudocode because that's what's expected on the exam. So I'm gonna try to like walk through this. So I mean, the most obvious thought that someone could come up with is just to be greedy, right? Always choose the maximum amount of profit for each given week for any office, right? So the first week you would be in SF, the second week you would be in New York, third week you'd be in New York, fourth week you would be in New York, and the fifth week you would be in SF. And this being greedy would not work in this case because there is like a cost to switch between cities, right? Um, so for example, let's see like a case where maybe like greedy algorithm would fail. So I mean, obviously, if you could do this in greedy, right, in one pass, that would be pretty efficient. But let's see. So when would this fail? Suppose I have my SF array and my New York array. Uh, this is, let's say, 800. Then the following week you can make 1,000. And here you can make 900. And the following week you could also make 900. Yeah. So here with the greedy approach, we're always going to take the maximum possible profit for a given week. So the first week we would fly down to New York and take 900. So that would be 900 minus the plane cost currently. And then what's the best one after that? Okay, we had to go back to San Francisco, so plus 1,000 for that week. and also minus 1000. So here, that simplifies down to negative 100. You're like losing money. While the most optimal solution would have been just to stay in SF and yeah, make 1,800. So simply, I don't think you can be naive about it like this. So let's try to think of this like more recursively, right? So we're trying to get the maximum profit for a given week, right? So, and there's n number of weeks. So what if we were to try to think about this like recursively, right? If we're at week number, like the first week, right? Week number 1. What is the maximum profit equal to? Well, you would either choose San Francisco, then try to take the maximum profit of whatever weeks come after it, right? Or it would be you take New York minus 100 and whatever the maximum profit comes after that week, after that, right? I could write that down. So, recursive. Let max profit at 0. Let's just think about it like the 0th case, like the start of the list. Let max profit of 0 be equal to the max of 2 decisions. The decision is either you're going to go work at New York in that case, or you're going to work at San Francisco in this case. And it would be the profit at 0 plus max profit for like a week moving on forward. So 1 in this case. Or it would be the max of New York at 0 plus max profit of 1. Yep. So this could potentially work, but one thing to be mindful of is we need to somehow differentiate between which city we're in, right? Right. Both of these are max profits right here. They can be the same functions doing the same thing. You need to differentiate between. Also, I forgot one thing. This should be a minus 1000 as well. But you need to differentiate between like the two recursive calls here. You can do that with adding another parameter, like a flag, saying like is SF in both cases, and here obviously it would be true. So you know inside of that function what to do. Or you can make 2 separate recursive functions and just call between both of them alternating wise. So right here you could have max profit of like SF, because you're in SF still. Or if you move to New York, it becomes max profit of New York. And what this we just defined here is max profit at week starting at week 0 at SF, starting at SF, right? Yep. So we're always making the assumption here that we're going to be at SF. So in that case, what we here actually defined is max profit SF. This function right here, the recursive part of the function. And if you want to describe max profit in New York, it would work the same way, except you'd flip the logic between one and the other. So here, instead of paying the $1,000 to do New York work, you flip that to be San Francisco. So right here. There you go. And yeah, these are the 2 recursive cases for both of the recursive functions. Now, if we're thinking about this like recursively, instead of saying max profit of 0, we could change this to max profit starting at I. And this more generalized approach makes it usable. Right? The max profit starting at I is always equal to it's choosing the best decision, either going to New York or San Francisco, and the max profit that comes after the week after that, right? So this is a nice generalization. And yeah, let me write this out once again in like English with like a precise definition of what max profit of SF of I represents, and New York too. So this means the max profit to earn at week I work starting being based in SF. Right. This is the precise definition of what max profit SF is doing. New York would basically be the same thing. I don't need to write it down, but yeah, so I think if you do this like recursively, we should be able to get this. So yeah, I'm gonna try coding this up real quick. And yeah, I guess before I can start coding up, I should talk about the base cases. I guess now that we have this like English definition, there's when do you think like this code will break? When do you think it will break? I believe it would break um, when you try to make a recursive call that is out of bounds of these SF and New York array. What was that? Suppose the size of these arrays is n. Well, if you're at n plus 1, it will be out of bounds. So we need to have a base case for that. That gives us insight about what the base case should be. So obviously, like common sense says, if you start off at week n plus 1, the maximum profit you can make between 0 to n has to be 0, because you can't work any days. So that would be our base case for both of our recursive functions. So here you would return 0 if I greater than n, and same for New York. There you go. Yeah, I think that basically defines this. I guess because of time interest, I think I'll just jump straight into the how to make this iterative, like using dynamic programming and speeding it up. So the most like I guess common trend to notice with dynamic programming is once you have like this precise recurrence definition, um, like right here, to figure out like how dynamic programming work, all it is basically evaluating like your recursive subproblems in the most optimal order, such that like if you're trying to answer one of the subproblems, you could already use like previously answered subproblems um, in some sort of like array-like structure. So you could simply look forward or behind or whatever order in your data structure that's storing these subproblems. And in this case, we notice like the subproblem max profit of I relies on max profit of I plus 1. If I have the answer to I plus 1, I have the answer to max profit of I by doing constant amount of work with this. So at max profit of this, SF of I, what do I rely on? Well, I rely on this answer. And what else? I rely on New York's answer as well. And if I have these two evaluated already, then I should be able to get the max profit of SF of I. Same applies for New York as well. So this gives us some insight about how to evaluate our subproblems. What's even more beneficial is that we know our base case is answers questions when we're out of bounds, when we're n plus 1 or greater, right? So maybe we could have this be our starting point to work our way back with DP. So if we have n plus 1, we have the answer to n, then we have answer to, n minus 1, etc. The thing is though, like, as I mentioned, SF relies on two subproblems. It relies on max profit of SF and also max profit of New York. So if you were to like think about this, how to do this with DP, you would have two separate arrays, right? You would have a DP of SF, and you'd also have a DP in New York. But how would you want to evaluate this? Well, we know the answers to both of them at n plus 1. But now, if you want to evaluate SF of n, you're able to, because you have the answers to SF of I plus 1 and also New York of I plus 1. So we can evaluate this. So let's just denote that with star. We solve this one. Same thing with New York. This one can be solved too. And once both of these are solved, we could go solve the previous SF one right here, because we have both of these solved, right? What I'm highlighting here. This one and this one. Therefore, we can use this one. So you'll notice like the evaluation is almost like a crisscross order, working our way from right to left. We're going to solve first some problem of SF, then for the same week the New York one, and we're going to work our way back like in crisscross order to get this to maximum profit. Yeah, I guess I could try coding it now real quickly. Yeah, hello. So def, I'm gonna also bring these notes in like comments. There you go. So def max profit. Let's call it max. Max profit. And what does it take in? Well, our algorithm is supposed to take in SF profits and New York profits. I don't know why it's italicizing it. Okay, yep. SF profit and New York profit. Yeah, let's go do this. Obviously, so we need to somehow make our like nice recursive function be translated into DP. So, like I mentioned, we could have like this DP array store my subproblems, and we evaluate them in crisscross order from right to left. And we know the answer to when we're out of bounds. We know the base case answer, so we're going to work our way back from there. So how many subproblems do we have then? Well, if there's n weeks, that means that we have n plus 1 subproblems. So let's make our DP SF be the size of n plus 1. What is n? It's the length of profit plus 1. Yeah. And I declared it everything to be 0. In that case, like I already by default set the n plus 1 value. Yep, DP in New York and DP of SF. And we're basically going to evaluate all this from right to left. So let's just go through this array in right to left. So we already have the answer to n plus 1, the length. Yeah, so let's do this. for I in range of, where do we want to start? So we already answered when we are at, answered like when we're out of bounds. So we need to start one level before, after that. So that would simply be the length of some array SF profit. You know what? Just to make it simpler, let's do DP of SF, right? We already have the answer to the last item, so we're gonna do start off at -2 of it, and we're gonna go all the way to 0. So this is how you reverse in Python. Yep, and let's go do these answers. So first things first, DP of SF of I is equal to the max of SF profit of I plus DPSF of I plus 1, or it's equal to New York profit of I plus max profit in New York, so DP of New York plus I plus 1, and plane ticket cost. Boom. We already answered this one. Now we can answer the New York one as well now. DP of New York. Yep, this is just crisscrossing. We're just crisscrossing right now. And this should give us that. Awesome. So I think our DP array should be filled up now. And if we want to get the maximum profit, once again, like start like from the beginning, right? We want it for week 0, right? So what is our initial state? We start off at San Francisco at week 0. So the answer to our max profit would be DP of SF at 0. Yep. And let's go try testing this really quickly. So let's say SF equals 800, 200, 500, 400, 112, 800, 200, 500, 400, 200, 500, 400. And what does New York equal? New York, I think it was like 200, 300, 300, 900, 700, 2000, 200. Yep, and print max profit of SF in New York. Alright, let's just quickly sanity check once again. I is going down, I plus 1, yada yada. Length of profit plus 1. Let's just try running it. 3,600. Look at that. Let's talk about this greedy one that we would fail at. Maybe let's try testing this out. Boom. Look at that. So I guess let's talk about the runtime now. So the runtime here would be obviously the number of sub-problems you have to evaluate, and each sub-problem takes constant amount of time to evaluate. And how many sub-problems are there? Well, there's n plus 1 here, and n plus 1 here. So 2n plus 2. So that would be big O of n. Linear time. You can do this in linear time. And the space would be the space of like these DP structure, because everything else doesn't grow with the size of input, and that would also be linear. So yeah, this is this runtime is linear, and space is also linear, and this is the most optimal solution to solve this problem.